of you. Very good morning. If you're watching me in the morning, otherwise, whatever it be. So, what I'm going to share with you is a problem shared by some of my students. You know, physics is infested with conservation laws. And if you've come all the way to rotational dynamics, you realize that the principle of conservation of angular momentum is pretty much pivotal towards problem solving of various kinds. Here's one problem. I thought, it was a simple problem, but cosmetically different. And those of you who are JEE aspirants would realize that essentially all JEE problems involve very simple, direct principles, except that they look a little different. This one problem, even though it's easy, I thought, it would do a world of good to you in terms of enhancing your understanding of the principle of conservation of angular momentum. It's just a different situation, but nothing difficult about it. So let me first share the problem with you. Let me tell you what the problem is all about. Here we have a rod AB, uniform rod AB of mass 1 kg and length 1 meter. Placed horizontally. And at time t equal to 0, the center of mass of this rod is given a velocity 10 meters per second at an angle 30 degrees with the horizontal. Gravity is in the downward direction. It's also imparted an angular velocity of 8 radians per second at this instant of time. Right? And there are two insects, P and Q, of mass 1/6 kg. They're initially at the center of mass of this rod. And with respect to the rod, along the rod, the moment the rod is launched, they start moving in opposite directions from the center of mass with a velocity of ½ meter per second with respect to the rod. Now, the problem wants us to find two things. One, the first part of the problem involves, you realize that this center of mass would undergo a parabolic trajectory under the influence of gravity. It'll be like projectile motion. After a while, this center of mass would come to the same horizontal level. And when that happens, we want to be able to find the angular velocity of the rod at that instant of time, one. And we also want to find the angle rotated by the rod by the time the center of mass acquires the same horizontal level. The angle rotated by the rod in such a time. All right. Now, see what is happening. When this rod is launched, the center of mass undergoes this trajectory. Unchanged. There is no reason for the center of mass to be influenced by anything else, right? And it's also rotating because of this omega. It's also rotating at 8 radians per second initially. After a while, the center of mass, let's say t seconds later, when it acquires this position, the rod would have tilted by a certain amount. With respect to the horizontal. And its angular velocity would have become omega at an instant of time t. Right? Let's figure out what this omega would be as a function of time. Right? Now, by the time this happens, this configuration of the rod is reached, the two insects P and Q would have moved r units away from the center of mass, and that r would be ½ into t, because ½ meter per second is the relative velocity of the insect with respect to the rod, and in t seconds it would have covered half of t meters. Now once that happens, would you want to believe that the system comprising the rod plus the two insects would have undergone a certain change? What change? Can you tell me what change? Think for a few seconds. Hey, when the insects were at the center of mass of the rod, and the rod was horizontal, right? The moment of inertia of the rod plus insect system, I1 in this state, when P and Q were both at the center of mass, the moment of inertia of the system, say I1, would have been simply the moment of inertia of the rod about the center of mass. I of the system about the center of mass would simply have been the moment of inertia of the rod alone, because the insects were at the center of mass. They would not have contributed to the moment of inertia. So, and that would have been simply 1/12 ml squared. L is the length of the rod, and so on and so forth. M is 1 unit, L is 1 unit. So, I1 would have been simply 1/12 SI units. 1/12. Right? Now, what transpires when the insects move away from the center of mass? Do you realize that the insects now start to contribute to moment of inertia? Right? For example, in this state, in addition to the rod, which has moment of inertia 1/12 ml squared, the insects contribute to moment of inertia. The mass of this insect into r squared plus mass of this insect into r squared. So there is enhancement in the moment of inertia, yes or no? So if moment of inertia grows, so I2, which is this state, what's the moment of inertia? The moment of inertia about the center of mass would be 1/12 ml squared for the rod, 1/12 ml squared for the rod, and the insects would have been, like the mass of each insect is 1/6 into r squared, and double it, 1 for each insect, right? So that would have been the revised moment of inertia about the center of mass of the system comprising the rod plus the two insects. Now, how much does it turn out to be? This turns out to be 1/12 plus this is 1/3 r squared. Yes or no? I hope you realize that. M is the mass of each insect, so m by 6 into r squared is the contribution to moment of inertia. So 1/3 mass is 1 into r squared. That's the revised moment of inertia of the system. Do you then see that there is growth in the moment of inertia? Which means that if there is increase in moment of inertia, what principle of physics would apply? What happens to omega? Would you in the first place want to believe that the angular momentum about the center of mass has no reason to change? The insects could move hither and thither. The rod could have its own motion. Under the influence of gravity, mg passes through this. In a system comprising the rod plus the two insects, the angular momentum of the system about the center of mass of the rod will remain preserved. How difficult is it to imagine that? Not at all. So, between this state and this state, can I effectively apply conservation of angular momentum? Yes. So let's do that. So we end up getting I1, the initial moment of inertia of the system about the center of mass, which is 1/12, into the omega of the rod, which is 8 radians per second, I1 into omega 1, right? That must be equal to the moment of inertia in this state, which is 1/12 plus r squared by 3 into the omega at this instant. How about it? Now, r I can write as half t. So that I have omega as a function of time available to me. So this can be written as 1/12 plus r squared, which is 1/4 t squared. So 1/12 t squared into omega. That's 8/12. Right? Now I can multiply it throughout by 12, and I end up getting omega equal to, that is omega as a function of time, omega of the rod as a function of time. Omega then turns out to be 8/1 plus t squared. Yes or no? Right? So I know omega of the rod as a function of time, and this is simply out of applying the principle of conservation of angular momentum about the center of mass. Now, this could also have been written as rate at which angular displacement occurs, d theta dt, right? And I can find theta as a function of time. How do I do that? D theta is 8 by 1 plus t squared into dt. I integrate this. When t is 0, which is this instant of time, theta is 0. When t is some t, let's say theta becomes some theta. So this will give me theta as a function of time. 1 by 1 plus t squared, when you integrate, you get tan inverse t. And that brings us to theta equal to 8 tan inverse t. 8 tan inverse t. So I know theta as a function of time. I know omega as a function of time. And now, what is it that I want? I want to know theta at an instant of time when the center of mass comes to this position. Now, how long does the center of mass come to this position? That's the total time of flight of the center of mass as in regular projectile. The total time of flight of the center of mass from this state to this state is going to be given by t equal to 2u sine theta by g. Yes or no? That's the total time of flight. So that brings us to u is 10. So that makes it 2 into 10 into sine 30 degrees divided by g, which is 10. Sine 30 degrees is half, so that makes it simply 1 second. That means in 1 second, this comes to this state. The center of mass comes to the same horizontal level. And in that time, by what angle would the rod have rotated? By an angle theta given by 8 tan inverse t. So the theta rotated by the rod would be given by 8 tan inverse capital T. Tan inverse 1, capital T is 1, so that makes it pi by 4. 8 into pi by 4, that makes it 2 pi radians. Right, good. That means the rod, in a time that the center of mass comes to the same horizontal level, would have again become horizontal, would have rotated by full 360 degrees, 2 pi radians. Right? Good. So that's the first part of the problem. And in this time, so this would have been, that means at this point, at the final point F, I'm talking of the center of mass being at F, the rod would have rotated 360 degrees. It would have been in this state. And the rod would have acquired a certain angular velocity at this instant. Let's say omega F is the angular velocity acquired by the rod. What's the angular velocity acquired by the rod in this time? Put t equal to 1. So that makes it 1 plus 1, 2. So that makes it 4 radians per second. So omega at this instant is 4 radians per second. 4 radians per second. Now, if the omega is 4 radians per second, the next part of the problem, which is about, after all, these insects are moving towards the ends of the rod. In some time, they would reach the ends of the rod. Right? In some time, they would reach the ends of the rod. When they reach the ends of the rod, when P and Q reach A and B respectively, what's the frictional force acting on the insects? Right? Okay. So, the insects have to cover half meter to reach B. And at the rate of half meter per second, so which means half a meter to be covered at the rate of half meter per second will take 1 second. That means in 1 second, 1 second is also the time that the center of mass covers the full range and the rod would have acquired a horizontal state. That means this is really the state where the insects would have also reached the ends P and Q. Insects would have also reached the ends P and Q. Half a meter to be covered at the rate of half meter per second with respect to the rod, the insects would have acquired this state. Now, very clearly, this is the insect, let's say, of mass 1/6 kg. And it has an angular velocity 4 radians per second with respect to the center of mass. Therefore, can I say that there is frictional force acting? There is frictional force acting on the insect, which will provide it the required centripetal force. Right? The frictional force acting on the insect, which would provide it the necessary centripetal force, is going to be given by mass of the insect into omega squared. Omega squared is 16 into the radius, which is half a meter, This is what happens, right? These many newtons, so that makes it 4 by 3 Newton. 4 by 3 Newton, right? So by the time you've come to the end of this problem, you would have realized that it was a good, nice application of the principle of conservation of angular momentum. Um, I would think that, problems of this kind that look cosmetically different can do a world of good to your confidence. This one I thought was a useful member of that set. Thank you so much. I'll keep dumping problems that look cosmetically different but are not difficult. So much for this time. Have fun and stay out of trouble. Bye-bye.